Log on, tune in, find out. Another good idea from Cambridge.
Before we start, can I just ask everybody to make sure their mobile phones are switched off? Recording equipment. So today is Stats Day. I'm very happy to introduce our first speaker. That sounds like a mobile phone that isn't switched off. First speaker is Michel Crucifix from Louvain, who will be talking about paleoclimate advances in the Newton Institute programme.
Thank you very much. So when the organizer kindly proposed me to present a talk for this closing workshop, this was 4 months or 5 months ago, there was an act of faith that the Isaac Newton Institute program would work well, that something would happen, and that we would have something to present at the end of this program about paleoclimates. And in fact, it did work well. There were a lot of groups of discussions, and in particular here, I would like really to make an account of what happened with a small group that formed with myself, John Tay, Richard Wilkinson, and also a lot of interaction and discussion with Vincent Garetta, John Hayslett, and Caitlin Buck. Obviously, that's not all about paleoclimate. There were many other things discussed about paleoclimate, but really the purpose of this talk is to take a very specific perspective, which is the dynamical system perspective. So we are looking really at how climate changes on a range of timescales that are of interest for paleoclimate studies. And so I will pose the problem and then use a very idealized setting, which most mathematicians know, which is the van der Pol oscillator, and show how it can be useful to do inferences about paleoclimates and conclude. So this really is the project that we ran during the Isaac Newton Institute. So putting things into context, this slide represents a proxy. What we call a proxy is some natural index for the evolution of climate over the last 5 million years. So look at the scale, 5 million years to the present. What the y-axis is not really important to understand this slide. It's a quite elaborate measure from sample from the deep oceans, and it has to do with benthic foraminifera. But the main thing is that you see that climate has a main trend, a main cooling trend, but it also oscillates. And these oscillations here are known as glacial interglacial cycles. To give you an idea, this is the last glacial maximum 20,000 years ago, and the climate was very different to today. I mean, on average, it was 5 degrees less than today, but the main thing is that the configuration of ice sheets, the concentration of CO2 and so on were drastically different to the modern. And through these changes, species evolve, and among them our species. So you came from the Ardipithecus, the Australopithecus, the Homo erectus, and us, and we are right here, so last glacial maximum more or less 20, 30,000 years ago. So we have a very recent species compared to the history of climate over the last 5 million years. So there has been some speculation that in fact the appearance of Homo erectus has to do with this change in climate. And a paper was published a few years ago where they recorded the climate of Africa using 2 of these proxies, so 2 of these indirect measures of climate. One is of Africa, of the Sahara and say Mauritania here, and one of Arabia. And what they recorded is the heterogeneous content of the deep sea record. So essentially they look at whether we mainly have sand, so an arid climate, or whether we have ground, so something that would represent a humid climate. And they characterized the evolution of this proxy over the last 3 million years. And although I wouldn't go into the detail of this slide, the numbers are probably too small to be read. The 3 million years and 0. They speculate about the fact that an increase in variability may have solicited our intelligence, our adaptation ability, and favored the emergence of more clever, more intelligent species, which was Homo erectus at that time. But changes in regime occur often, and even if you look at the more recent past, but recent here is 800,000 years ago, scientists are now able to record the evolution of CO2 over that period, thanks to mainly the huge effort of people drilling ice cores, and especially in Antarctica. So we owe this record to an old project, the Vostok drilling, and a more recent one, a European project for ice core drilling in Antarctica. And when they first observed the evolution of CO2 over the last 800,000 years, so time is running leftwards, they observed that apparently, visually, the pattern of changes, the pattern changed around 400,000 years ago. And there is a name for that. This is called the mid-Bruns event, the mid-Bruns change in regime. And this is a record that is mainly inferred from another proxy, the deuterium. This is called here temperature, but you really should see it as proxy. And again, you do see that there is apparently a change in regime. So even closer to us, and I would like to thank John T. Rougier for having prepared this slide. There will be a few slides from my colleagues, John T. and Richard, throughout this presentation. If you consider the last 100,000 years, and this is, again, time running rightwards in this case, this is another proxy. This is the delta 18. No, I wouldn't explain what it is exactly, but this is sampled in Greenland. And in 1988, well, I don't quite remember the date, Willy Dansgaard published a paper showing these very rapid variations, and they are now known as Dansgaard-Oeschger events. And again, you see a lot of quite important transitions, many recorded in Greenland, but they had effects on life, and especially on methane concentrations as well. That's the reason why they can be recorded everywhere, with the final transition towards the Holocene, which is a stable climate, or more stable climate that we had over the last 100,000 years, and which also had an impact on the development of our civilizations. So our problem really is to really characterize, to understand these variations. Why do we have changes in regime? Where are they located? Are we heading towards a new change in regime? So to answer these questions, we have raw material. And this raw material may be qualified as climate sensors. So essentially, if you go toward the Earth, you can sample records of various nature. You have ice core records, deep sea records, you have heterogeneous records, loess as well, which you can sample in China. You have speleothem. You have a whole range, a zoo of information, but which is always very indirect information about changes in climate. Recently, Nick Lang and Eric Wolf published in Climate of the Past Discussion a collection of a good dozen of records which they think is very good material to study the climate evolution over the last 1 million years. And I would certainly recommend reading that paper because it gives you an overview of what sort of information is available. There are obviously many other papers about paleoclimate data, but this one is a good synthesis. So a problem really is to understand climate. And one way to model climate dynamics, is to consider a dynamical system, to consider it as a dynamical system. So essentially, very schematically, the representation you may have about climate is, about your model, is the following one. Climate clearly is influenced by changes in the Earth orbit. This gave rise to the astronomical theory of paleoclimates, according to which glacial and interglacial cycles are caused, in that theory, by changes in the Earth orbit around the Sun, as well as Earth's obliquity. The obliquity is the angle between the ecliptic and the equator. So the mental representation you may have about the problem is the following one. So you have these changes in orbit and in obliquity, which are a forcing on climate, which you represent as a dynamical system. So a number of components which interact together, and they don't interact instantaneously, and they have their own dynamics, and so they can have their own resonance mode, they dissipate energy, and so on. And from that dynamical system, you measure a various number of observations. Well, you do a number of observations, sorry. Essentially, you have sensors of that dynamical system. So these ideas are presented, well, perhaps with a more focus on the more recent past, in a paper actually presently in presentation, led by Caitlin Butt, Tamsin Edwards, and many other people. And this is part of a supranet network, which also had a good tribune here during the Isaac Newton Institute. So a problem really is to identify this dynamical system. What is it? To calibrate it means you will propose this dynamical system and include in that dynamical system a number of parameters for which you may have priors and posteriors. Essentially, you calibrate the dynamical system. And then you have to operate a selection. If you have various models of paleoclimate, what is the best one? Which is the one that will help you to predict, for example, the next major change in regime? So which one is the most trustworthy? And finally, you also, I mean, as a mathematician, you may have a lot of fun in analyzing the bifurcation properties of the dynamical system and so on. Oh, how do we construct the dynamical system? And I will just here show a slide of a very general setting, a very general theory. So generally, you represent the state of the system you want to study, any complex system, as a vector of components that evolve through time. I mean, when you have a general circulation model, for example, I mean, all the x are all the temperature, pressure, humidity at all grid sources. You can have many of such variables. And you can also have very simple systems. I mean, biologists study the neuronal responses with just a couple of variables, even though a neuron can be a very complex thing. And the hope is to be able to write a number of equations that are differential equations. Essentially, the variation through time is expressed as a function of all the other variables, t and parameters. If you're lucky enough, you can organize your equations such that they have different characteristic time scales, and this is the rule of the tau I have written here, tau 1, tau 2, tau n, with the idea that the fastest modes can be eliminated. The dynamical, I mean, some physicists call this adiabatic elimination. It's a weird name, I find it. So essentially, you will assume that this is equal to 0, and you suppress one equation, and so you gain a little bit of simplicity. So now what people quickly realize is that this is not enough. You also need to account for unresolved phenomena using random numbers, so noise processes. And I would certainly recommend a paper by Majda. I see that Christian and David Cromlin are here, who published in PNAS a paper where they really show how you can do this adiabatic elimination in presence of stochastic processes. Although the overall idea of writing such equation is not new. Paleoclimate scientists usually refer to an old paper by Hasselmann in 1976. But really, for the paleoclimate context, you should look at paper by Barry Salzman and Bob Marsh in 1991, where they really presented that setup adapted to calculate the evolution of climate over long time scales. Perhaps a bit more concrete than equations, a curve. So this is precisely 3 realizations of the model by Barry Salzman and Bob Marsh. This is an evolution of an ice volume. So this is an ice volume anomaly compared to a standard, so don't be surprised to have positive and negative numbers. And I've made the scale here with large positive ice volume on the bottom of the scale to match the first curve about climate evolution I showed you earlier in this talk. And given that the model is stochastic, so there is some noise in it, if you run the model 3 times, you have 3 different responses. And so in one case, you have the blue one, you can have the red curve, or even the black curve. What does it mean for a statistician? How does a statistician see that curve? What does he learn? Well, he would probably say that there is a very complex joint structure between the climate states at various times. So essentially what it means is that, consider the red one here. I mean, the red climate 500,000 years ago is deglaciated. This is an interglacial. And this is compatible, that climate is compatible with an interglacial 10,000 years before. So there is a joint structure between the state of climate at different times. So it's not enough to say climate here is uncertain, it can be anything. You have to go deeper in your description of the uncertainty. You have to say, well, we have a number of possible realizations. We have a number of possible paleoclimate histories. Each of these paleoclimate histories is self-consistent. Together, they create a range of uncertainty about our knowledge of climate. On the other hand, all these paleoclimate histories have something in common. There is clearly a change in regime here, more or less 1.5 million years ago, which is in fact hard. I mean, the reason for this bifurcation is in fact embedded in the equations used by Salzman. Although it didn't write explicitly, it was 1.5 million years ago. So what I mean is that you have major transitions that seems to be robust, and then a number of possible paleoclimate histories that are compatible with that history, with these constraints. But that's not it. That's not it. If you want to compare it with paleoclimate data, you need to cross one step further and think about the process that will link climate to your observations. So the statistician here urges us to write a model that will make the transition, the link between climate and what you actually observe. And what you actually observe is, for example, delta 18O as a function of depth. It's not climate as a function of time. So you need to do that transition. And although I don't certainly want to overload you with useless equations, because these are really useless, but it's just to show that if you write a very simple model that converts time into depth and then converts climate into, for example, delta and 18O, you can simulate series of potential observations. And this is what is shown here. So now you realize what is the problem we are facing. You have to decide whether a model that generates this is compatible with actual paleoclimate observations. And you also have to use that framework to update your knowledge on parameters, to update your priors on parameters, as well as to predict further bifurcations in climate. So how do we do? The first thing to think about, and this is really one thing that was stressed during this Isaac Newton Institute, is to think about model discrepancy. So you can generate billions of paleoclimate histories with that model. You will never have one single realization that exactly matches, I mean, at the two near digits, your observations. So no model will perfectly reproduce the observation. We know that. I mean, climate is extraordinarily complex. The observations are so, they're complex themselves. They are indirect measures of climate, so you can't expect to reproduce climate exactly. So you need a layer of modeling between model and reality. And this layer, statisticians call this modeling discrepancy, modeling the difference between your model and reality. And there are, in fact, various ways of modeling discrepancy. You can decide to do that very explicitly. For example, you can say, okay, I will use a stochastic parameterization to represent uncertainty, to represent discrepancy. And as Tim Palmer told us briefly yesterday, this can be a cute way of doing things, but it can also be dangerous. Sometimes, by doing a stochastic parameterization, you can draw your model away from reality even further. You have to be careful with it. It's a way of modeling discrepancy. It's not the only one. You can also play with your likelihood function. So remember, or for non-statisticians, the likelihood is the probability of observing what you have observed given your model and the priors on model parameters. And in that likelihood, you can fiddle your likelihood to account for model discrepancy. So you can allow, in fact, a distance between what your model simulates and what you actually observe. And this distance is a representation of model discrepancy. There is yet another way of modeling of considering model discrepancy is using approximate Bayesian computation, and we'll focus on that a little bit later. So for example, you can say model discrepancies at different time steps are normal, identically distributed over time. This is an example of model discrepancy. And the message here, the thing I got from this program at the Isaac Newton Institute, is that depending on what you want to focus on, what is your interest, you may have to be careful with how you model your discrepancy. If you are interested in the dynamical structure, or if you're interested in changes in regimes, which is really the purpose of this talk, the effect of astronomical forcing, the noise structure, some choices of model discrepancy will just destroy precious information. So you have to be careful about how you formulate discrepancy, because once adopted, the sentence is scrambled here, but I mean these assumptions about discrepancy influence subsequent inferences, including model selection. The reason for the octopus is just between Jonty and me. It doesn't go further. Anyway, let's illustrate all of that using a concrete example, even though it may look simple, the van der Pol oscillator. So mathematicians know the van der Pol oscillator. It's a small dynamical system written in the 1920s to study the response of some electronic system. And here are the equations. Are a little bit changed compared to the classical van der Pol oscillator. I'm slightly appalled because the graph was much more contrasted on my screen, and I appreciate it doesn't show very well on the slide. I probably need a little bit of blackboard here. Try to see what we can do. Anyway, the climate is here represented, or the system, after all, is represented with two variables, x and y. So we don't have x1, x2, xn, we just have two of them. But the structure is the same. You have a first equation that tells you that dx over t, dt, is just y plus a parameter beta plus f of t. And f of t is the astronomical forcing. It's something that changes over time. So if you just consider that first equation, it has a stable state, or steady state, when y equals minus beta minus gamma ft. So if you consider two axes, so y and x, you can not very well see them, but you can guess them. The blue curve is y equals minus beta, and given that it can do plus or minus and plus gamma f of t, this stable state will oscillate between minus beta minus gamma ft plus beta gamma ft, and ft changes over time. So if there is no forcing, essentially, you should be around this curve if you're at steady state. So now consider the other manifold. It's more interesting. So this dy over dt multiplied by some factor equals minus y cubed minus y over 3 minus x plus some noise. First, neglect the noise. Then the steady state implies that x equal y to the power 3 minus y over 3. And this is this red manifold here. So what it means is that if you are at steady state, you should be at the same time on the blue manifold, because it's the first equation, and on the red manifold, because it's the second equation. So you should be here. And the property of that point is that it is unstable. It is an unstable steady state. So as soon as you leave it, and this was the purpose of the vector field, which unfortunately doesn't show well on screen, it shows it to show you that you will be driven away from that stable state. So now there will be a constant competition between these two equations. And this is now the role of alpha. Alpha can be very large, 20, 30, which in practice means that the time scale of response of this red manifold is much shorter that the time scale of response compared to this slower manifold. So what it means in practice is that you will spend most of your time on the red curve. And so what will happen is that you will oscillate, come here, spend time on this slow manifold, and then suddenly jump back to the other branch of the slow manifold, and so on. So you live in a limit cycle. And van der Pol knew that very well. What I'm telling you here is a theory that is 80 years old. So now, more interesting, if you move beta, you will arrive at a stage where the intersection between the blue curve and the red curve will be a stable point. So then you have crossed from an oscillating regime to a stable regime. And this crossing is known by dynamicists as a Hopf bifurcation. Near the Hopf bifurcation, you will have more interesting phenomena. You have, for example, excitable phenomena, which means that you are normally at a stable equilibrium, but if you knock out a little bit, you can be sent to a cycle, which will take some time because you need to go to this branch and then oscillate back. And so you can go through a whole cycle of glacial interglacial, if you wish, or this branch to that branch over a certain characteristic time, and then go back at rest to your stable state. So in fact, what happens is that the palette of behaviors exhibited by a system like this one is much richer than you may think when you just consider these two simple equations. And things become even more complicated when you consider forcing, an oscillating forcing, and noise. So the funny thing is that you can have some interpretation of that system in terms of climate. Consider the first equation. What it tells us is that the derivative of x is essentially a drift plus the forcing plus some other influence by other components of the climate system. This is exactly what people, tenants of the Milankovitch theory, believe the ice volume should respond. And the ice volume integrates variations in the astronomical forcing. This is exactly what it does. And it's also influenced by other processes, like, for example, the ocean circulation. And on the other hand, consider this other equation. What it tells you, in fact, is that you have two stable states and two stable branches for that manifold. Exactly how people believe the ocean circulation may behave. And so you can already start considering some coupling between these two equations that may represent some dynamics of climate. And so it's therefore no surprise that many of the conceptual models of glacial and interglacial cycles that have been proposed over the last 20 or 30 years, in fact, have that dynamical structure. So what changes is that some say, no, this is in fact CO2, or some say this is in fact sea ice. You have a number of interpretations about what X and Y should be. But fundamentally, the dynamical core of these equations all come back to this van der Pol oscillator. And we are trying really to demonstrate that with a postdoc working in my team, really that, for example, a Salzman model is really nothing else than a van der Pol oscillator. You have to do it hard because the equation, you start from 3 equations instead of 2, and the nonlinearities are not located at the same place. But really, topologically speaking, it's the same model. So, funnily, if you choose well your parameters, you choose well tau, alpha, and so on, you may reproduce the benthic curve, so the astronomical, the observations over the last 800,000 years. So this, for example, represents the climate evolution over the last 700,000 years, 0 and even a simulation into the future. The blue dots are observations, and the red, the black curve, is the simulation with the van der Pol oscillator. There is no magic here. I mean, I really had to play myself by hand to choose the parameters that work. But nonetheless, you do have a model response that resembles the paleoclimate record. And we will consider it as our basis. The red curve is the astronomical forcing, and the gray curve, which again doesn't show well on the slide, I'm afraid, is the Y. So what I said would represent the ocean circulation, for example. you can certainly criticize that model, and we just use it as a first example of a modeling target. So now what happens is that you can now play and consider the influence of noise. So this is what we do now. So consider that model and add a little bit of noise. The black curve here is just this one, so it is exactly the same deterministic model. The red curve is the one realization, one possible realization of the same model plus the stochastic forcing. And what you observe here is that at some critical times in the past, you've in fact switched from one possible climate history to another possible climate history. Remember the Salzman model, we showed that there were possible climate histories throughout the Pleistocene. So the effect of noise, in fact, is to send you from one possible realization of the climate system to another possible climate realization of the climate, one other possible realization of the climate system. And again, dynamicists know that very well. This is called a phase slip. It's a bit more subtle here, because a phase slip is a vocabulary that has been developed for systems that are forced by a periodic forcing. And in our case, look at the astronomical forcing over here. It's not periodic at all. It's a quite complex signal. And in fact, if you do a spectral analysis of the astronomical forcing, you do have a lot of rays, a lot of spectral lines that represent the effect of precession, and I call them P1, P2, P3, which are groups of frequencies related to the effect of precession, and to obliquity. So when you want to study the bifurcation structure of the van der Pol oscillator driven by the astronomical forcing, you have to think of fairly sophisticated mathematical techniques and vocabulary. So one thing we did during the Isaac Newton Institute is to study the number of, I have to use the word, it's the cardinality of the pullback attractor. So what it means is you just look at the number of possible climate histories compatible with the equation. And this is represented on the right-hand side. So essentially this is tau, so this is the natural frequency of the climate system. Gamma is the amplitude of the forcing. Those who are used to dynamical systems may recognize Arnold tongues. And what happens is that you do have a lot of possible synchronization regimes that originate from the various precession and obliquity lines. This is a complex graphic, and I don't have the time to really go into the details of it. But what it says is that depending on the amplitude of the forcing and the natural frequency of the climate system, you may lock on 1 gray, 2 blue, 3 red possible climate histories. And phase slips will occur when you live very, very close to boundaries between two different colors. But there are many such boundaries if you look at this. And so you are quite likely to experience a phase slip at some stage, at some time, if the climate system is indeed compatible with a van der Pol oscillator. Okay. So now, so what it means, a phase slip? It means that a perturbation, a volcanic eruption, or some human spreading, something like that, may change the future of climate very durably. Okay. So now the problem is to do inferences with that. So inference essentially is about updating priors, for example on parameters. There is a number of parameters in that equation, using observations. So this is what statisticians would call calibration. It's a little bit more than tuning. Tuning is what I did previously. So you try and you tune the knobs, you turn the knobs until, oh wow, you got focus and I have exactly what I wanted to. Calibrating is more smart than that. It's really about inferring distributions, or at least inferring means and variances from some physical constraints, from a model, and from observations. The equation looks simple. Essentially, this is the Bayes probability formula, what it says that the probability of your stochastic parameter being equal to theta given observation is a likelihood, probability of observing what you've observed if the model is correct, multiplied by the prior and divided by a marginal likelihood. So this simple equation looks very simple. but in fact it's not easy, it's not really tractable. One slide that Richard Wilkinson, who is not with us today, but this is a slide that he prepared during the Isaac Newton Institute, was this one. What he did is he first produced pseudo observations with the van der Pol oscillator and added some noise to them. And he says, okay, suppose my model is correct, these observations may be these ones. And then he produced this graphic where, and I'm afraid the label of the x-axis disappeared in my using his slides and embedding it in my slideshow. This is tau, so this is the natural frequency, and this is alpha. And you can see that the structure of the likelihood is very complex with a lot of local minima and a lot of local maxima. And so it seems of showing that inferring likelihood or inferring updating parameters may be a very complicated task. And then in some email exchanges, Jonty said, well, I have simply no idea what one would try to fit, a simple deterministic dynamical model to real data. Because this asked him authorization to code him. He was very glad I would do it. So this, in fact, was produced using the deterministic system. So the problem we have really is to apply this formula in presence of a stochastic dynamical system, which is even more complex. But again, statisticians have devised a way of doing that. And one way of doing it is to use the particle filter. So what is the particle filter? It's like a Kalman filter, if you like, but which is more adapted to complex distributions. And again, this is a slide prepared by Jonty with a lot of bees. And people do love that. So suppose that you have a number of possible climate states. And they're all represented by these bees. You are at time t minus 1, say, and then you cross a step to time t. So you propagate, you use your stochastic dynamical system to propagate the swarm from t minus 1 to t equal t. Obviously, all the bees will evolve, and it's a stochastic dynamical system, so the bees will fiddle around. And then you can weight each of these bees using the likelihood. And remember, the likelihood is also the right place to account for error observations, but also model and discrepancy if you want to. So these bees will all get different weights, and the whole thing about importance sampling is that you will be able to redistribute all these bees in order to have a new swarm where all bees have equal weight and distributed according to the posterior distribution. And so you propagate your swarm from t minus 1 to t plus 1 and so on through time. And the particle filter is a quite good way of getting an estimation of the state as constraints are added through time. And so the idea of Liu and West, which I am quoting here in 2001, is to use the particle filter also to update your knowledge on parameters. So essentially, and very roughly speaking, you augment your state vector with a number of parameters, and then you have to make a lot of tricks to account for the fact that the parameters are constant while the state variables are not constant. And when Jonty first came in Louvain, 2 or 3 years ago, he really was very helpful because he coded all the particle filter for parameter and state estimation. And we tried that with some of the Salzman's model. And we even published a paper in 2009 saying, oh, it's wonderful, it works well. We have found a way of calibrating paleoclimatodynamical system. And in fact, 2 years later, we realized that we have been trapped. We did a mistake. In fact, our priors were quite narrow. And so consequently, you don't learn anything about the dynamical system itself. You just assume a priori that your model is correct, that your priors are narrow enough, and you just update your priors. But if you take wide priors, and here the exercise is made again using the van der Pol oscillator, then the particle filter fails. And consider, for example, distributions of parameters. This is tau, and you have a wide prior to begin with. We know that the real value is around 20. So you have this wide prior, and suddenly, at the first abrupt deglaciation, so blue are data, and this is a deglaciation, Well, the particle filter just collapses, it degenerates. And nonetheless, here I use 100,000 particles. I could try with 1 million, but it means that the computing time becomes also quite expensive. So we are probably not going to a good method here. And even though some parameters sound like converging, this accident here is quite dreadful and quite alarming. So we thought of using other methods. And this is really the purpose of the Isaac Newton Institute program. So then Richard Wilkins, oh yes, well I just show here that if you do a forecast with the calibrated model, you just get nonsense. You have a number of possible future of ice volume, but they oscillate very gently. It doesn't look like glacial and interglacial cycles anymore. So we probably didn't do a good job in updating our knowledge on the climate system. So then Richard Wilkinson interacted with us and told us, well, why don't you use approximate Bayesian computation? It may be useful for you. And this is just a copy-paste of one of the slides he showed 2 months ago during his seminar. So it's a little bit out of context, but I thought I would still put it to tell you what is the angle of attack of the problem. And the angle of attack of the problem is to say this. Well, think of your model. What do you want it to capture after all? You don't think that your model will reproduce exactly the data, don't you? It's two equations, and the paleoclimate is such a huge thing. So if you build such a model, it's because you have some idea, some preconceived idea in mind. It's because you want to capture certain aspects of the climate system. Probably want to capture that you have glacial inception, and then a slow buildup of ice, and then an abrupt deglaciation. Probably want to capture that. Or you also probably want to capture the main period of glacial and interglacial cycles. So why don't you rate your model according to this specific criteria? And at least it will be calibrated to reproduce that, and you will obviously get some constraints about how it may evolve in the future. You have to be careful when you play that game, obviously, because it means that you're extracting certain aspects of your model. So you are restricting the amount of information used for calibration, and the whole thing is to find a good trade-off between the complexity of your model and the amount of information you use to constrain it. And that's the whole thing of Bayesian, approximate Bayesian computation. So what you do, you consider a distance between the realization of your model and the observations. And in this case, what he chooses to use is, where is it written? Okay, here, the number of crossings of 0. So you have glacial and interglacial cycles and cross 0 by the x and y trajectories, and also have another criteria which we are not sure we agree using that, but that's the initial condition. Anyway, so the intercomparison exercise here with the particle filter is not perfect because it did the experiment with slightly different scaling of parameters and slightly different experimental conditions. So we are not here heading towards a very neat intercomparison exercise between approximate Bayesian computation and particle filter, but nonetheless, Richard, and again this is a slide by him, showed that you can effectively, in a twin experiment, so you first generate pseudo observations and then look whether you can calibrate on these pseudo observations. You can indeed calibrate a number of parameters. The red line here is the true value, and the distribution with the histogram is the posterior, and the posterior indeed captures the true value. What does it mean? When you do that, when you consider a simple metric, you bypass the way of, you bypass the specification of a likelihood. And in fact, all your model discrepancy assumptions are made implicit by the fact that you focus on a distance metric. So you really choose to focus on some aspects of your model and distrust other aspects of your model, although this selection is quite implicit. So now there is a third way of tackling the problem. And here I'm passing on to John T. again, which is the particle marginal metropolis Hastings algorithm. Well, it happens that in Bristol University and in the mathematical department, School of Statistics is the right way of calling it, they are quite state-of-the-art about Bayesian calibration, and especially Bayesian calibration of stochastic dynamical system. And there is one researcher there, Christophe Andrieux, who is really passionate about this question of calibrating dynamical systems or stochastic dynamical system. And so he devised a method which is called the particle marginal metropolis Hastings algorithm. And so what it is, again, this is a copy-paste of a slide by John Tin. I will try to express it with my own words. We have seen that you have different ways of using the particle filter. You can use the particle filter to update your knowledge about the state vector. And one byproduct of sweeping the observation is that you get a marginal likelihood for the parameters you have used. And there is another way, which is to directly use it to update the parameters. And we have seen that updating the parameters is not helpful in our case. So the idea of Christophe Andrieux is to say this. Let's use the particle filter to sweep the observation and estimate the likelihood. And then you use a metropolis Hastings algorithm. So you do essentially random walk to try to find, you wander in your parameter space and try to find the area where the marginal likelihood is largest for these parameters. And then ergodically, you will wander in the area which corresponds to the posterior on the distribution. It's not a simple algorithm, and there are a lot of fiddles and tricks to gain computing time, and I will certainly not go into the details of that, but this slide speaks for itself. So these are the 1, 2, 3, 4, 5 parameters. The red line is considered to be the true value. Again, this is a twin experiment. So Genty first produced pseudo data using these true values, and then he tried to calibrate the system and see whether he could recover these true values. These are the various steps of the metropolis Hastings algorithm of the PMMH method, and you should wander around these true values. It's exactly what you do here. And again, if you look at the distributions, they do converge to the true values. It is a real success. Obviously, we are not over. And this is what we did during the Isaac Newton Institute program, so my talk is coming to an end. And it's probably time to think about perspectives and how we will continue in the future. So first, what we did. So we think that we can use a dynamical skeleton to model paleoclimate dynamics. I promised myself I would say a few more words about how we construct this dynamical system, and I just forgot to do it during the talk. What we have opted here is for a quite phenomenological approach. You just guess the equations and see whether they work. But obviously we are physicists, and we also would like to get this equation really emerging from some more physical principles, and I will just say a few words about that in a minute. Now, the dynamical skeleton needs to be linked to a paleoclimate data. Caitlin Buck would probably call them sensors with Bayesian framework, within a Bayesian framework. And calibration is not simple, and which method you use really depends on what you want to learn. So what we learned during this Newton Institute program, first it was a real think tank, and it was so educative and so rewarding to me about model discrepancy. What is the likelihood? I'm still not sure I understand what is the likelihood. How we use statistical summaries. The number of crossings is called a statistical summary. We launched an intercomparison exercise between different methods. We also are heading towards concrete application. I will say a few more words about that in a minute. And we also had good exchanges about datation models, which I just ignored during this talk. So what we should do now? First, we have to think better about the equations. Van der Pol oscillator, you've seen two manifold. In fact, it's probably possible to extract information about the structure of these manifolds by doing systematic experiments with climate simulators or with ice-sheet dynamic simulators. So we can probably recover the bifurcation structure of these manifolds using more grounded, more, deeply rooted physical principles. And it's where emulators will be useful. But I will just give John T. The possibility of speaking more about emulators. We have to consider additional timescale interactions. We haven't considered at all the effect of Danz-Garage oscillations, and there are real speculations about the fact that they do influence the dynamics of glacial and interglacial cycles. We have to consider dating uncertainties, and we have made a few steps towards that, but that's not over. And we also have to go towards specific applications. And this is another thing for which the Isaac Newton Institute was useful. In fact, when I was here, I was visited by a colleague working in Oxford University, looking at deep sea cores, and I mean, this is Rosalind Rickaby, and she was really fascinated by all what you can do with this simple dynamical system, how you can calibrate them and probably also reject or accept models, or at least select models. And I mean, she took half a day explaining me her ideas about how the carbonate compensation mechanism work, and we are probably heading towards really trying to write a model that would accommodate her hypothesis and test it against real data. So this happened because I was here as well, and she was close to here. Well, she's in Oxford. Do you consider Oxford is close to Cambridge? I don't know. That's anyway. And so we have to do more about model calibration and identification. So we'll certainly polish this intercomparison exercise we launched and consider further statistical summaries. There is with me my PhD student Guillaume Lenoir, who is fascinated by wavelets and would like to see whether there is a way of grouping these various concepts. Thank you very much for your attention.
Okay, so we've got almost 10 minutes for questions and discussion before coffee. Cecile?
Yes, thank you for a very nice talk.
Thank you.
I would like to point out that there's quite a bit of literature that is a little more general than the modern view of adiabatic elimination, where the Wiener process is not just added, but is rather a result of multi-scale interaction.
That would be interesting, because I was asking myself when preparing the slides yesterday, I was really comfortable having this omega dot at the very end. I'm glad to hear that. So yes, if we can use coffee time maybe, and you give me some references, I would be interested. Thank you.
Is it the failure of the particle filter? Can you associate it with the fast-slow structure?
So exactly that. I mean, the particle filter is like a short-circuit driver. He learns to drive by looking time step after time step. And then when it just suddenly turns, ooh, what happens? What I've learned so far, because I learned to drive in a straight line, and suddenly it turns. What's happening? He loses most of the information capitalized, accumulated during the regime during which it was driving on the straight line. So that's the thing about the particle filter in that configuration, so for parameter and state estimation, is that it just doesn't see the big picture. And our brains do see the big picture instantaneously because we do see patterns. The particle filter doesn't see patterns.
So we're still smarter than Jonty's bees.
What do you want to estimate? You want to estimate the coarse grain part of your system, right?
Mm-hmm.
So the question actually is whether you want to do the weights based on a homogenized particle. And that may have worked because then you're taking the scales into consideration when you're putting the weights on. So this may be something that you may listen tomorrow.
Okay, so you're speaking about that tomorrow. Okay, I'm looking forward to it.
Scales
Mhm.
work with what?
We should just clarify here that we used a very, very basic particle filtering notation with no bells and whistles at this stage. So we had an opportunity maybe to go an order of magnitude larger on the state vector, so that because we've got a lot of resources in here.
I'm very taken with your number of crossings as a statistic. What you want, of course, is for that to be a sufficient statistic. But my take on it, and I face very similar problems in my area, a huge computational problem. My take on it is that I've got something very similar to your crossing number, an almost sufficient statistic, in the sense that once you've sucked out that bit of information, there's almost nothing left. You've almost wrung your dishcloth dry. But I don't have any more intelligent way to think about it than almost sufficient. I'm toying with the idea of defining it as sufficient, in the sense that I am not interested in the residual information left in my sample. Is that an intelligent thing to say?
I don't know whether it's intelligent, but it's a way I see things. And it's funny when you do a talk, you really appreciate all the weaknesses of what you explain, and you do need to do the talk to appreciate them. And I was just thinking about that. Obviously, the number of crossings is not a sufficient statistic. You don't capture all your system with the number of crossings. So there are probably many ways of tuning the model and getting the same number of crossings. But, so what you have to hope, but this is a gray area and my ideas are not clear on that, is that you are capturing what you need to know. So to some extent you are implicitly saying that what is not the number of crossing is useless, or at least is not trustworthy, and that you will not, you do the act of faith that you will not use the model for something else. I do appreciate, we need more deep thinking about it.
I will cite your papers when I'm advancing my method.
If I could actually comment on that, I think sufficient statistics are perhaps not a very helpful way to think about it, because sufficient statistics arise in the context of a likelihood, which is a completely specified probability distribution. And the whole point about this kind of thing is you know that the models you're using are very simplified versions of reality, and they have little artifacts that you don't want to capture. So to some extent, when you're using these kind of things, what you want to do is to use the probability model to take the bits from it that you want and to avoid the rest of it. So sufficiency is not quite the right way to go.
I know, that's what I was asking.
Yeah, but what I would say is that there are strong links between approximate Bayesian computation and something called generalized method of moments, which is a method of inference where you simply try and match observed with modeled properties that are carefully selected. And there's a lot of literature in econometrics on that topic and how to select properties and how to weight them and all the rest of it. And I think there's some scope for looking into that.
Yeah, thank you very much for this very illuminating talk. I think it was very well done. And my thinking is more on the equation that you use, which should have a better physical basis. And it looks like your equation is capable of getting the 400 or 700,000 years ago to today oscillations, but not the transition to 1.5 million year, right? And why do you think is that? And do you need 3 equations to get the 1.5 million transition, in your opinion?
Okay, in fact...
Yeah, why did you choose a nonlinearity of the cube?
No, I have to tell you my whole story about that. And when I started 5 years ago on that project, I read Barry Saltzman's book. This was my bedtime book. And Barry Saltzman wrote 3 equations with giving them physical insight. He wrote, we have ice, and the variation of ice volume is a function of temperature. But temperature is adiabatically in equilibrium with ice volume and CO2. And so he wrote with pages and pages and pages of development, he wrote it as a function of CO2, ice volume, and a variable that he called ocean circulation. And then say, okay, but CO2 must vary because a whole set of processes. And he wrote a full paper listing that depends on sea ice, on ocean circulation, with a lot of arguments. Some are phenomenological, some are inferred from experiments with geoscience. And so he has this complete equation. And then he said, well, ocean circulation is probably a function of ice volume, and it's a function of, I can't remember what was the other, circulation itself, and it was something like that. Anyway, I had only 3 equations. And the thing when I present a talk with exactly the particle filter applied to that system, it has 8 or 9 parameters. It's a large number of parameters. To Michel Gill in Paris 2 years ago, he told me, what you are showing, it's just a van der Pol oscillator. Okay, maybe. And I just get back to the Guckenheimer and Holmes book, use the van der Pol oscillator, tuned it, and I got the Benthic curve. So it's just to say that, in fact, you don't even need 3 equations, you need 2 of them. I'm not meaning that the van der Pol oscillator is the physics of climate. I'm just saying that it's a good start to learn about calibration and priors and posteriors. But what it also learned to me is that the van der Pol oscillator may be understood as interactions between different manifolds. I mean, this red curve and this blue curve represent different, to some extent, they are the response structure of different subsystems. Another hope I'm having is that if you are doing smart experiments, you have to design experiment plans of experiments with a good ice sheet model. I mean, state of the art, they are developing some in Bristol, in Grenoble. So I'm visiting these people and ask them, can you do a set of experiments that will enable me to learn me about, probably not, it's just not the S, it's probably something more complex, but there is a manifold in there. And then if I'm speculating about what is the structure of the ocean circulation, but we do have papers, we do have experiments, a plan of experiments with ocean circulation, you may maybe end up with a theory written in terms of a small number of equations in which you will be able to understand the connections between various manifolds. So essentially various components of the climate system. So this is the start. And I'm not claiming this is the physics of the climate system. I'm just saying it's a good, small system, well documented, about which libraries have been written, and that allow me to start with the problem.
Okay. I think I'm going to chair ruthlessly this morning, and we're at 10:30, so it's time for a half-hour coffee break. But before we go, should we thank Michel again for it?